Hi, good morning, everyone, or good afternoon if you're ahead of me in the time zone. Um, I hope everyone is able to hear me clearly and also see the video. Can someone please confirm in the chat?
Yes, I can hear. I can see your slide.
Am I audible? Thank you. Sure. Yeah. So, thank you for signing up and joining me today. And we're just going to wait for a couple more minutes to let everyone in, and then we'll start. Just a minute or so more so that everyone is able to join. All right, so let's begin because there's a lot to cover. So thank you once again for joining me today. My name is Farhan, and this session is all about what self-driving cars are, what is the current state of the art in self-driving car software development, and then how do you get started? Where do you get started if you are interested in the field? Uh, so a little bit about me. I'm a software engineer, and then so I was a software engineer for about 7 8 years, and then I turned to education. So I'm in the ed tech industry right now. But other than that, I'm interested in self-driving cars, working on my own. So I like to experiment with stuff, in simulators using deep learning and deep reinforcement learning, just to see what is possible and what is not. And I like working in the simulators and bringing like having the simulator data and also bringing in real world data into the simulator, because we have all these high fidelity simulators now where the distinction between simulation and real world is very thin now. So I believe that simulators are an extremely good platform for any sort of experimentation that you want to do with self-driving cars versus building a real self-driving car. So simulator is where most of my work happens, and this session is up, almost going to be about 90 minutes long. So I'll try to cover everything in 1.5 hours, and then we'll have a 15-minute long Q&A at the end. There is a live quiz. So we have a bunch of questions, general questions about self-driving cars and the field. So the live quiz is here. You can see the link on the slide. I'm also going to share the link in the chat box. So you can keep this link open in the tab perhaps, and as and when we reach this point, I'll let you know that this question, and I'm waiting for your responses, and then I'll give everyone like a couple of minutes to see if they can answer it. Just fun stuff, nothing very theoretical. So moving on, what the session is about. So we'll start with what you know because the session is about autonomous cars, self-driving cars. So we are going to have a close look at what autonomous cars are, how the hardware is different from a regular car, and then because we are going to talk about software, we will see what the software stacks looks like, what are the different components that make up the software stack of a self-driving car, and then we will sort of zoom in and look at the algorithms that make up each component. So like an overview of the algorithms, not a deep dive. And then we are going to talk about some of the challenges that we face when we build such algorithms, and all then we are going to move on to how AI is being used, and I'll cover what I mean by AI later, but how AI is being used to solve some of those challenges, and how far we are, how far we have progressed in solving those challenges. And then in the last section, we are going to look at the tools, the data sets, simulators, courses, and everything that you can use to, sort of get up to speed if you're interested in, self-driving cars, whether it's research, whether it's hand-on practice. So there's something for everyone. So to begin with, we are going to look at the hardware, like I said. So if you look, there's a lot of these sketches out there in the media and everywhere, but what you roughly see is, if you're looking at a self-driving car, so uh, you know you have this car which has, what is most evident is the sensor suite, which is maybe lidars and cameras sitting on the roof of the car or sitting behind the windshield. But there are other components, like there could be radars which are sort of hidden behind the bumper, and there could be additional processing power computers which would be hidden in the trunk. There might be additional cameras or radars hidden in the rear view mirrors and so on. So one is the sensor suite of the car that sets an autonomous car apart from a regular car. The other thing which is not so visible to us is the electronic components. So almost all cars today have a mix of electronic and mechanical controls, like brakes, gears, accelerator, and everything. When you press a gas pedal, or when you try to turn the steering wheel, there's some electronics sitting behind the steering wheel that helps you in making that turn. So maybe it provides you additional torque, maybe this it provides a safety mechanism, but there is some electronics. The sort of difference between the electronics in a regular car versus a self-driving car is just how much, what sort of controls you can do electronically. So in a regular car, like I said, it's a mix of mechanical couplings. For example, the steering wheel will have something connecting it to the axles, but in a self-driving car, most of these systems can also be purely electronically controlled. And what happens is, if you have purely electronic system, then you can pretty much hook it up to a CPU or a controller of some sort, and you can control everything electronically. So your car sort of becomes a big remote control toy that you can control, o- using cables or over the air, or howsoever you like. But basically, the control is hands free. It doesn't require direct human intervention. The other thing I want to mention is that a lot of these independent electronic components, they are hooked together, they are connected together, using different types of networks. And uh, on most cars, there is a way to tap into that network and send the commands to different components. So on a regular car too, you should be able to just look at the data that is flowing over the network that connects different electronic components in the car. But not only can you look at the data, you can also send data to different components and make them behave in different ways. So you can electronically start the car, you can change transmission, you can apply brakes and all sort of stuff. uh, but yeah, this varies from in lower end cars, most many of the controls will be won't you won't be able to control them electronically. But on high-end cars and anything which you want to convert into an autonomous car, the controls have to be electronically manipulated. Right. So that's about the hardware. If you look, so that was like a silhouette or an outline of what the car looks like. A real car will look something like this. You can see there's an Uber ATG, experimental vehicle. You see a lidar sitting at the top. There's a camera array sitting right beneath it, and there's a lot of other stuff that is not visible. But on the left, you can see that this is what a lidar looks like if you were to look like very close enough. This is a small Velodyne lidar. And then there's a camera. Camera again comes in different variations, and we are going to see some of them. But the general idea is that this is the sensor suite that sets apart the self-driving car. And there could be multiple sensors of the same time. So one car will typically have many different radars, many different cameras, because if each of them will have slightly different characteristics. And we'll talk about them a little later. So just going a little bit deeper into the sensor suite. So why do we need so many sensors? And we're going to come back to this later on as well. But the whole idea is that unlike humans, humans have a very evolved ability to reason about things and to understand things, to perceive things, and that is super important to be able to drive safely. Machines don't. That is where we are struggling, and we'll talk about that. But machines don't. So to compensate for that lack of reasoning, you can make up for some of it using more advanced sensors. So for example, not only we use cameras which offer you a vision based perception, you can also have lidars, which is like it can also provide you depth information. And you can also use radars, which gives you information about which objects are moving and how fast they're moving. uh, and you also want to have this sort of redundancy because of the characteristics of the characteristics vary a lot across these sensors. So the first thing we are interested in is spatial resolution, because this is how you make sense of the environment. So if you look at a camera image or a video feed coming from a typical camera, it's very high, it's very dense. The resolution is very dense. You can make out where the objects are, what those objects are. You can see their color, you can see their outline. You cannot directly tell, or the algorithm cannot directly tell the distances and velocities of those objects, but they are like crisp and vivid to begin with. But if you look at a lidar, the output of a lidar, which you see in the center, it is much sparser. So it's pretty much like a camera, but the sort of points that make up the image, they are more spread out. They're not so dense, and so with the naked eye, it's a little difficult, quite difficult actually, to make out what objects are present in the lidar data. Also lidar, naturally it doesn't have any sort of color information. The color information could be added by software to so that you have understanding of the depth, but there is no point having color information in lidar image. So it's difficult to make out what objects are present, but lidar does give us additional information, which is the depth information, which is very important for driving. And then radar also has a low resolution. So typically a radar image will radar output will have blobs representing every objects. So you don't even see the outlines of the objects. That will of course vary from radar to radar, but generally you don't get a very precise outline. The good thing about radar is, yeah, I'll come to that, but it works in all sorts of weathers. It can see across fog and cloud and stuff. So those are the qualities on the positive side. Uh, in terms of you know uh, why you need these different sensors, so like I said, lidar can measure distances directly, radar can directly measure velocity. You can also measure distance with the lidar, and then as the distance changes, you get an idea of how fast an object is moving. But that involves some mathematics, and that also involves some error that creeps in at every stage. So that is why you want both a lidar and a radar. All right. So that's a sort of an overview of why you need different sensors. Now I'm going to pause here for a minute or two. So we have our first quiz coming up, and I would like everyone to attempt to answer it. So the quiz is: which of these sensors can directly measure velocity, right? So we know lidar cannot, but camera, radar, which of these sensors can directly measure velocity? So if you go to the same link that I shared earlier, and I'm going to share once again, right? So there are four different options here, and the question is which one can directly measure velocity?
Hi, Fahang.
Yeah.
So I have one question. For LiDAR, do we need to have extra equipment on top of the car? And is the size of it big? Uh,
You don't need extra equipment other than the lidar itself, which of course has to be placed, somewhere on the car so that it can look around. Because I haven't spoken about it, but lidar has a sensor that has to scan the area. So
okay,
like the these big radars that you must have seen that ATC uses for air traffic. So it has to keep revolving and collecting data from all directions. So it has to have that line of sight in every direction.
okay. And could
And
we say that the camera and the radar, both of them, if we combine both of them, that can also already cover the all categories, all the necessary information. So
right,
LiDAR is
they do.
actually not necessary.
Right, you are right. So I'll touch upon that a little later. Why? I mean, some
Mm-hmm.
companies definitely believe that lidar is not at all necessary. They are not using
Mm-hmm.
lidars at all. So I'll come to
Mm-hmm.
that. Yeah,
Okay, sense.
thank you. All right. So sort of going to stop the quiz here and reveal the answers. So the right answer, of course, is radar, which I also sort of happened to mention earlier. So radar is the only one. It uses the Doppler effect. So it sends out, electromagnetic waves, and then those waves bounce off the objects. And there's a frequency change when things bounce off objects that are moving. And that frequency change, from that frequency change, sort of you can calculate how fast they are moving and in which direction they happen to be moving. So radar is the only one that can do that. All right. So let's talk a little bit about, because I mentioned that the talk is about how AI is being used. I want to sort of talk about autonomy first. So there are two types of systems basically. One are autonomous systems, and then you have systems which we call automatic systems. So what you see here on the slide is an example of both. So your washing machine, which can be completely automatic. So how automatic? So you can just feed the laundry, and then theoretically at least it can guess how much detergent is needed, what should be the right water temperature, how many cycles are needed, what should be the RPM at which you know the drum rotates. So all of that can be calculated by the a typical washing machine. And on the right hand side, you have a car, which we are calling an autonomous system. So I just want to spend a minute or two to understand what the difference is. So if we talk about the washing machine, you can see on the left that there are a bunch of sensors. So there could be water hardness sensor, there could be water temperature sensor, there could be weight sensors, humidity sensors, all sorts of sensors. On the car too, you have sensors, so radars, lidars, and everything. So what is the difference between a car and a washing machine? That we call one of these an autonomous system, and the other is an automatic system. Uh, what when we think about it, I think there are two major differences. One is the sensing or the perception part. So the washing machine sensor, if you think about it, is pretty straightforward. These are small cheap sensors, and the major distinction is that they can directly measure something. So a water temperature sensor will directly give you what is the a reading of the water temperature, right? And perhaps it will require some software processing, but you can almost use the raw data. It doesn't require a lot of processing. Similarly, the weight sensor can directly give you the weight, and the humidity sensor can give you the humidity. On the other hand, if you talk about the sensors on a car, a lidar or even a camera will give you an image, but we are not interested in an image because we want to make decisions based on what the sensor readings are, what the output of the sensors are. We want to have finer grained information, right? Like what is present in that image, what objects are present, how are they oriented, how are they moving, stuff like that, and that requires very complex processing. So, in terms of perception or sensing, this is a major difference. The other part is decision making or planning, which is simple in case of an automatic system like car. So decision making would, decisions like how fast the drum should rotate and how long it should rotate. These are straightforward. These can be formulated as equations. These can be coded as if then else conditions in programming language. But the decision making for a car is much more complex, right? So how fast you should go? Are there pedestrians on the road? Is the road ahead clear? If there's a traffic light, what color the traffic light is? So these are complex decisions, and then that is the other part, which is the major difference between the two, right? And so what where AI fits in all of this is, solving the problem of complex perception and complex planning, right? So both of these. And so AI is a broad term, like people use it for all sort of things, but here in this context, we are using AI to club together all those algorithms that we will use to solve, complex perception and complex planning. So any algorithm that gives us near human or, better than human performance on any of these tasks we are going to talk about a little later. So we'll call that, club that under the head of AI. And of course, these have to be at least as good as the human drivers for, self-driving cars to make sense at all. So, just how much AI, what sort of algorithms we need, that depends on how much autonomy you need. There is this 5, 6 level, variation, different variants of autonomy. So, not going into details, but on the left is no autonomy at all, where the human driver is driving. Then you have some systems like the ADAS systems on cars, which basically assist the driver in some way. So, in lane keeping or, stuff like that, or maybe parking, so they can assist the driver, but the driver has to be hands-on all the time. And then you have different levels, and on the extreme right you have level 5 where no driver is needed at all. So any car which is, as smart as a human being, that wouldn't probably require a human being behind the steering wheel. So that is what is needed. And so obviously, like, if you are aiming for level 3, the type of AI algorithms you would need is very different from what you would need for level 5. Or it could be the same algorithm or the same type of technology, but for level 5 it has to be much more robust and much more sophisticated than level 3, right? And I'll go into a few of these details a little later on. So, so to begin with, we have to understand what is the problem that, people have been trying to solve. So, how is self-driving, is autonomous driving any different from regular driving, and if so, how? So, let's look at a very high-level view of what autonomous driving or even human driving is all about. So, the first problem when it comes to driving is localization, which is just understanding where we are, where the car is, or where we are as human beings on a map. This is technically called localization. For humans, we look at a map or we know from our own experience or knowledge where we are. Not a big problem for us, but for the car it turns out to be quite a problem. The second problem then is route planning, which is knowing if we are here and we want to go there, how which route we should take, which roads we should take, and stuff like that. Again, for humans, is you sort of have a mental map, or you can always use Google Map or something like that to plan the route. Uh, Vehicles also use a similar approach, but there are a few nuances, and I'll talk about that. Then comes perception, like understanding. So you are in the car, you know where you are, you know where you want to be, and you know the route, and then you want to see what else is there around you. So which are the vehicles, how fast they're moving, are there pedestrians, all the stuff, traffic lights, everything. Perception is just making sense of the surroundings, everything in your environment, right? And once you have all this information about your surroundings, the next step is obviously prediction, which is also important because you not only want to understand what is the current state of the environment around you, You also want to understand how's the environment going to look like, uh, let's say a couple of seconds later, because that is how you plan, that is how you plan ahead of time. So prediction is also super important. uh, we of course know, we don't do exact calculations in our brain, but we are able to infer, uh, we are able to predict uh, very accurately. So the predictions are good enough that we don't crash into someone or some vehicle, because we didn't predict their behavior correctly. And then comes planning, which is essentially deciding what we want to do, which is going, where do we want to go in the next few seconds. And then control is basically executing the plan that from the previous step. So which, like, do you want to apply brakes or accelerate or change gears or turn lanes, or so not turn lanes but turn the steering, stuff like that. And then additionally there could be, you can think that there's a sort of extra layer which is just supervising that everything is working correctly, right? So this is the problem that we solve as human beings, and then self-driving cars also sort of solve a replica of this problem. Now, again, I'm going to pause for a minute or two, and I have another question. The question is, which of these steps, so we have localization, route planning, perception, prediction, and everything, which of these steps is the most complex one to solve? Which one do you think is the most complex one? You can again take the quiz at the same link. So again, going to pause for a couple of minutes. And there are five options. Number one is centimeter level localization, then prediction, planning, perception, and control. So which of these is, in your opinion, the most difficult one to solve computationally? Yep, answers are pouring in. We still have like a minute left. So I think this is a public link. There shouldn't be an issue opening it, because I see the link working for many of you. Not quite sure. If you're facing issues opening the link, you can perhaps try a different browser, because I'm using Chrome and this seems to be working. Right. So, most of you are still answering. So I'll just wait for another minute. Right. And think of it like, which one should be the most like, when you think of, which one should be the most complex one, think of all the other autonomous systems that we have. So we haven't been building a lot of self-driving cars, but there are autonomous rovers, for example, for, on the Martian surface or on the moon and stuff like that. Yep. So I think I'll reveal the answers now. So, you know, the truth is that perception is the most difficult one. We'll see why. But if perception, they say, is the biggest hurdle, if you solve perception, then you have solved self-driving cars. So we'll go one by one, from localization to the other stages. So localization, as I said, is understanding where we are on the map. The only difference is that in case of self-driving cars, you have to be extra precise in how you localize things. So it's not okay just to know where you are, which location you are. Like you have to be extra precise, and the precision has to be of the order of a few centimeters. So for humans, it's probably okay to know, like, I'm on this road roughly at this place. But for the cars to drive safely, and you can very well understand if there are two cars next to each other in different lanes, you don't even want them to brush against each other. Then the precision has to be of the order of a few centimeters. And basically, the question that perception asks is, what is our position, and then what is our heading. So most of the and so basically, cars also use GPS like us to find out where they are, but we'll see how exactly they improve on the accuracy. But the GPS tells them where they are and in which direction they are headed. Challenges, like I said, is the main challenge is the level of accuracy that you get from a typical GPS. But there are other issues like signal absorption, reflection, and there. So another sensor that gets used other than the GPS is an IMU, which is an abbreviation for an inertial measurement unit. An IMU is basically an accelerometer and a gyroscope in one package, and what it tells you is how much you're accelerating linearly, like in one direction, and what is your angular acceleration, like if you're taking a turn about some axis, so what is your angular acceleration. And we'll see how IMU is used to for localization. But essentially, you need two sensors, GPS and IMU. One of the other things to be aware of is that the GPS uh, update rate is sort of low when it comes to self-driving cars. So typically it will be something like say 1 to 10 hertz, which means it gets refreshed every 100 milliseconds. Right, there's a gap of 100 milliseconds between two consecutive refreshes. And if a car is moving really fast, let's say 80 miles, 100 miles, then it could have moved several meters between two refreshes. And that is something we have to aware of, and that is something we have sort of have to solve, which is so it is also one of the challenges that you have to solve. uh, IMUs can be pretty fast, they can be instantaneous. The only issue with IMUs is that they directly measure acceleration, they don't measure your position, so they cannot be used. You cannot get your absolute position on the map, but you can estimate how much you have moved, between two time steps. Uh, but that also has to be done through integration, because the IMU will tell you how much your acceleration is, and then you have to integrate the acceleration to get the velocity, and integrate again to get the displacement. And of course, this is numerical integration, so all sorts of errors creep in. So you have to be aware of that. So that's about localization. Uh, Route planning is sort of simple, like I mentioned. So again, self-driving cars can also use maps like we do. The difference comes in the sort of detail that is included in those maps. So when a self-driving car uh, requires routing information, it requires a lot more semantics. What do I mean by semantics? So for a self-driving car, it's not enough to know that it has to take a certain road if it has to go from position A to location A to location B. It also has to know uh, you know which lanes to take in which part of the journey. So for example, if you have to enter a highway and then you have to exit at some point, it has to know that you have to be in certain lanes to be able to safely enter and exit. And then if it has to, for example, take a u-turn somewhere, it has to know which lanes are the right lanes to take the u-turn. So a lot more semantics are needed. And uh, yeah, so basically cars need a much more precise route planning as well, and I'll talk about a little bit of the semantic stuff a little later on. But the difference is that you need an additional semantic layer, and the more information you have in that semantic layer in your map, the easier it gets for other components, right? So again, I'm going to pause for a second, and there's another quiz. So one of the things that I didn't mention is high definition map. So when I talk about semantics, like stuff like this, which lanes are present and which lanes are okay to take turn, which lanes are closed perhaps temporarily. So these are all semantics that are not generally not present in a typical map. And there could be a lot of other information that can help self-driving cars, like which might seem silly to us as human beings. For example, where exactly, if you have to find the location of a traffic light at an intersection. So where exactly do you look for the traffic light? Now we as human beings know where the traffic light is. We can spot it in a fraction of a second. But for self-driving cars, this is also a difficult problem. So sometimes one of the approaches is to create an HD map which will include semantic information like this. So it's a high definition map which has additional semantic information. So this quiz number 3, which I'm going to open up now, is about HD maps. And right. So the question is, which of the functions, there are 4 functions listed there. So which of the functions cannot benefit from HD maps? And HD maps are maps which have these additional semantic information in them. So again, like pausing for a minute or two. Cool. So I'll reveal the answers rather quickly in the interest of time. So the correct answer for this one is D, which is control. And so we saw that control sits at the bottom of the stack, right? And I'll tell you how the other 3 benefit. So for example, the first option was localization. Uh, in a moment, when we come to localization, what sort of algorithms you use for localization, we'll see how localization benefits from HD maps. Planning definitely, because we were talking about route planning. So planning definitely benefits from HD maps because you have this additional semantic information there. And the third option was perception. Perception, I didn't directly mention perception, but perception benefits from HD maps because if you know where to look for certain objects, so you can be doubly sure, you can have that additional information included in your routed to your algorithm. For example, if I'm trying to identify where what color the traffic light is right now, I could be looking all over the place, or using a HD map, I know exactly where to look for the traffic lights, and then I could just use a simple algorithm that can detect color variations to detect what the color light, what the light of the color is. So control does not directly benefit from HD maps. All right. So we have talked about localization and route planning. Route planning is similar to what humans do, but yeah, we need more semantic information. Now let's come to perception. Perception, we saw in the quiz that is the hardest part to solve. Some people say that it's like 90% of the uh, problem of building a self-driving car. And perception, like we saw, is identifying everything that is there in the surrounding, right? And what do I mean by that? So it could be things like what objects are there, which is object detection, like traffic light and vehicles and stuff. Not only that, but you also want to understand how much space they are occupying or where exactly they are, uh, you know, in the larger scene. So which is sort of trying to identify the object and then also creating a bounding box for that object. Sometimes you also want to understand the exact outlines of the object, right? So if it's a tree, for example, you can create a bounding box, so you know how much space the tree is occupying, but that bounding box sort of also covers unnecessary areas outside the tree. But if you could have a more precise boundary, uh, you know which is called semantic segmentation. So if you can precisely segment objects in a scene like humans do, then that is more beneficial. So sometimes you also need semantic segmentation. And then free space detection is also sort of perception, because when you have all the objects and everything detected and identified, then you want to understand how much free space is available for the car to navigate. So that is also perception. Now, the challenges is identifying the objects, which we know that like it's been it's been an open problem for a long, long time. Computer vision has evolved. There are algorithms to identify simple objects. There are deep learning, networks that can identify thousands of objects with pretty high descent accuracy. But human level accuracy, getting there is really difficult. Also, we want to identify objects at the right granularity, and also in the right context, and that is the more challenging parts. Like there are networks which can identify deep learning networks or neural networks which can identify thousands of objects, but they still do that in isolation. They don't look at the overall context most of the time. So what you see here on the left hand side at the bottom is a truck, a Samsung truck perhaps. And what we can tell in a split second is that this truck has some sort of a display at the back, and that display sort of projects some information which the truck is able to look at, but which vehicles which are following the truck in the same lane may not be able to look at. And we can quickly understand that this is to help anyone who is behind the truck, so they can look at this display and they can tell what is ahead of the truck. So if you want to change lanes, or if you want to go around the truck, then you can look at the display and decide. But this is certainly going, this is a big challenge for any algorithm. This is going to confuse the algorithm, because the algorithm, all the algorithm sees is perhaps another car in the display, and then it is puzzled as like there's a truck and this car inside the truck, or what is happening. The algorithm can't tell. So it's stuff like this where you need additional context. This very easily fools an algorithm. So perception is, you can sort of say that perception is the only unsolved part of the stack. The every other part, localization, planning, and everything, that can be done very accurately, but perception, we are still lacking, and it's an open problem. And perception has to be like 100% accurate before you can safely drive. So it is an open problem right now. And granularity is also important, which I mentioned earlier. So what do I mean by that? So when you're looking at the scene, if you look at a tree, you don't want to start counting the leaves in the tree. You don't want to identify individual leaves. You just want to say that this tree out there is, by the road. So that is also something we are very good at, but the algorithms have to be trained. So trained, or it is it, is still an open problem to like figure that out. So and going back to when we were talking about sensors, this is why you need more sensors. So if you cannot tell every detail from just looking at the scene, looking at a camera image, then perhaps you need to make up for it using other sensors, and that is why lidar and radar sort of help. And sometimes you also need depth cameras. Right. So that was perception, the big open problem. After perception comes prediction. Prediction is like just estimating what the environment is going to look like down the line, a few seconds down the line. uh, how do we predict? We just sort of a mental model of the behavior of everything, so we can look at a vehicle, how fast it is moving, and we can safely predict vehicle would have moved, whether it would have turned or not, and stuff like that. For cars, self-driving systems, it has to be again very precise. So they have to use sensor data, and they have to use uh, perhaps the laws of physics to accurately predict where every object is going to be. This is again challenging sometimes. So you can use laws of physics and everything, but for example, if you want to predict the behavior of a human being, so if you see someone who is just standing on the sidewalk maybe, and you know there's a potential that in the in a fraction of a second they might just be on the road in front of the self-driving vehicle, then for a human being it's very sort of easy to judge that there's a potential for harm and start to decelerate. But for an algorithm it is very difficult to predict behavior like that. So we'll see how people are attempting to solve that as well. And part of the prediction, solving the prediction challenge, is tracking, which is just keeping track of, which is keeping track of every object over time, and that is how you make predictions, right? So you can take the radar output, or you can take the camera image, you can identify objects, but then you also have to track them across camera frames or across the radar refreshes. So you know that this is the same object, and you know that how they have been behaving in the last few milliseconds, and that is how you predict how they will behave in the next few milliseconds. So these are some of those challenges, and we'll see how they're being solved. uh, yeah. So especially when you're trying to solve the prop challenge of predicting human behavior, you have to look for very subtle cues, like is the human where are they looking and how they're moving, pose and everything. So you get subtle cues from there, and we'll see how those can be exploited. Then comes planning. So planning is just basically having a trajectory to follow in the next few seconds, in terms of if computationally what you need is some sort of curve which takes you from point A to point B in the next few whatever your time horizon is. It could be a second, it could be a couple of seconds, but that is essentially. So computationally it looks like a simple problem. You have to come up with a feasible curve that doesn't intersect with your trajectory of any other vehicle. uh, some of the challenges are just feasibility, like whether they are intersecting, whether a collision might happen because of following that trajectory or not. But there are additional challenges like figuring out if a trajectory is comfortable enough or not, because there are human passengers in the car. So obviously a self-driving car has to move in a fashion that is comfortable. You don't want to have a lot of sudden acceleration, whether it's longitudinal or sideways. So that is definitely you know something we have to watch out for. So comfort is also something, and one of the challenges is how do you quantify comfort. So if you have a trajectory, how do you even measure how comfortable it is? Then there's of course safety, and the last challenge, which is here on the slide, is just formulating everything as a single number. Because if you have, let's say, a bunch of trajectories and you want to identify which one is the best one, then you want to rate every trajectory, and for that you need a number, right? So right here I'm going to pause for another minute, and this time the question is, so you see a trajectory on the image here, right? The green trajectory which supposedly will take us around the truck and ahead of it. So is that trajectory safe or not? That is the question. So I'm going to make the question live, and there are only three options: yes, no, or can't say. Yep. This is very interesting. Some people are saying it is safe, some are saying they can say. Right. Is it safe or is it not? Yep. So again, I'm going to reveal the answers, and the correct answer is C, which is you cannot say. Uh, I'll just, you know, yeah. So why can't be safe or not? Seems to be safe. The thing is that we are just looking at the space, right? So at this point of time, it seems safe, but you also have to bear in mind that the truck ahead of us is also moving. So when you cut back into the right lane, you cannot be 100% sure that the truck will still, like, there would still be some gap between you and the truck behind you, right? And likewise, when you are trying to enter the center lane, there could be another vehicle coming in, in the same lane from the backside. So you cannot be 100% sure. So one of the challenges with planning is that planning has to happen not only in space but in time too, right? So any algorithm that has to plan its safe trajectory, it has to plan the x and y coordinates in both space and time. Right. So that was planning. Control is sort of straightforward. Control is just like we have the plan. We saw the trajectory. If that trajectory is safe, then how do you follow that trajectory? So how much acceleration, how much braking and steering and everything is required. The key challenges here is number one, there's always a latency between the time you plan something and between the time you apply a control and between the time that control actually controls the car. So there are different latencies in different parts of the system. So you have to sort of have a good understanding. And as human drivers, when we are learning to get us become a driver, so we sort of get an intuition of how much that latency is, right? And for an algorithm too, it has to either estimate the latency from data, or it has to, that latency, the worst case latency, has to be sort of hard coded somewhere. uh, and the challenge is tuning the algorithm. So these algorithms will, essentially what these algorithms do is you have a desired trajectory that the planning stage gives you, and then you have a current trajectory which you can just measure using the sensors. And these algorithms, the control algorithms, they try to apply controls so that this your actual trajectory is best aligned with your desired trajectory, right? And so there are a few knobs that you have to turn, some tuning required. So that tuning is also a challenge in the control stage. And of course, the third major challenge is the physical constraints of the vehicle. So you have to be aware of the range of the different controls, um, and that is also something which can either be hard coded or it can be estimated, right? So we saw what the sort of problem looks like that we are trying to solve. Now the question arises, so we have been hearing about self-driving cars and how they're going to hit the road in 2018 and 2020 and so on. So uh, why why don't we see a lot of self-driving cars right now everywhere? And the sort of answer is that perception is the open problem right now. If you solve perception, then you will have widespread self-driving cars everywhere. But there is also issues with safety. So algorithms, it's very hard, like I said, to predict human behavior, both the driver and the people outside. And you can build a system which works 99% of the time, but there are always, those 1% cases which are very difficult to solve. And we don't have, an easy way to solve them, like all the edge cases, and I'll come to some of them. But those are the edge cases are difficult to solve. Otherwise you can say that we already have self-driving car. There is also the issue of urban versus highway driving, and so both have their challenges, and the challenges are different. So if someone is building a self-driving car which is doing pretty well in an urban environment, may not do equally well on a highway, and then the other way around as well. So basically, the issue with perception is that there's a long tail of object detection for first of all. So you cannot say you are very good at detecting thousand types of objects, but what if you see a different object uh, on a day, and then how does the car react to it if that object is not something it has seen before? Uh, and then actually very simple issues like identifying a stop sign. Stop sign is just an object, and identifying it is just an object detection problem. But that stop sign there can be so many variations of it, right? It could be mounted somewhere, it could have slightly different colors, orientation, partially hidden or occluded. uh, Sometimes you would see people holding a stop sign if there's some construction or something going on, and then they could be holding it upright or it could be down, and those signal different things. And so all of those variations, they are hard to get right for an algorithm. So that is one challenge that remains open. And we already talked about context and the level of detail or granularity. So uh, those are still open challenges. Now what has happened is that with, for example, with deep learning and collecting a lot of data, and uh, you training your algorithms over and over and again, uh, you can get you can cover every new edge case, but in the end it's still a fragile system. So you can, from 1,000 objects, you can go to 1,000 objects, but you know there are still new objects out there. And you see one such example here on the left, this tail light. So we have normal tail lamps and we have these new generation tail lamps. I don't know exactly what they are called, but they happen to sort of animate from left to right or right to left when you have the turn indicator on. Now this is something new for an algorithm. So how does the algorithm, like we as human beings are able to logically reason, but there's no way the algorithm is going to figure out on its own that this is just another tail lamp. So that is difficult. The algorithm cannot do that, but what people are trying instead is to at least build something which can identify whenever there's a new object, right? So whenever there's an object that the algorithm hasn't seen before, it is at least able to raise an alarm, and then uh, we sort of can handle it. If there's a human driver, they can handle it, or we can at least look at the data later on and then update the algorithms. And there's another case at the bottom where you have some birds, large birds and animals on the road. That is also something that falls under the category of those edge cases. So that also needs to be solved for. Uh, so before we move on, I just wanted to mention a few of the other variations of the problem. Like we talked about the self-driving car problem being a spectrum of things, not a specific problem. So first of all, someone mentioned that we don't really need lidars. So that is a debate that is going on. So whether or not lidars are needed, and lidars also have their shortcomings because any like cameras as well. So whenever the weather is not right, and you know, so lidars have a hard time operating, and of course the resolution is also not as good as cameras. So do we really need lidars or not? That remains an open problem. Some companies like Tesla and Comma.ai, they're using a purely vision and deep learning based approach. So they don't even have lidars installed, while majority of the companies like Google and Baidu and Cruise and everyone else, they are still using lidar data, and they are fusing that data with radar data and camera data basically. The other sort of interesting question is whether you use more deep learning, which is, like I said, so deep learning is easy to improve if you don't know about a new object, or if you want to have different variations. You can, with more data, you can just collect more data and you can improve your algorithm. With computer vision, it has to be years and years or decades of improvement before you can get better. But deep learning systems are black boxes. It's very hard to debug them. It's even very hard to test them and put some sort of number, like you can say that you can't say with confidence in which conditions they will perform correctly. So that raises like computer vision or deep learning or a mix. Most companies started with a largely computer vision based approach, but some of them, notably Nvidia, have been introducing a lot of deep learning into their systems, and that seems to be working. Highway versus urban, we already touched upon. The other variation is geofenced versus general purpose driving. So some of the companies are toying with the idea of having a full-fledged autonomous system where you don't require a driver, but then you are just driving within a restricted area, and you know the area so well that you have every little detail figured out. Perhaps you have high quality HD maps that get updated quickly, and perhaps also you are not driving at the sort of speeds that you would drive at in any general area. So there's a talk that I'll mention later, but you know this variation is also there. And then just how much of high definition maps do you need, because there are companies like Baidu which are betting big time on high definition maps. So if you have every little detail in the map, then your decision making and your perception gets a lot easier, right? The last quiz we talked about. So but this remains fragile, because then you cannot generalize. You need a high definition map, and then those high definition maps have to get updated whenever there is any update to the environment. So uh, other companies are purely taking a visual approach, where you try to identify the objects without needing much context from the map. So moving on, we know what the different what the different problems are that we're trying to solve. So if you look at a typical software stack for a car, this is how it looks like. So there's a perception module, there's a prediction module, routing, planning, localization, and they are interconnected, some of them feeding data to others. And so these problems can be solved in isolation, but at runtime they have to interact with each other. The other important thing is that they don't all of them don't run at the same frequency. Some like localization will be relatively slow, some like perception and prediction have to be relatively faster going. So that is also something we have to take care of. So now let's go back to how people are solving localization. So localization is just getting your position and heading. The input to a localization module will be something like a GPS, the reading from a GPS receiver, which gives you the position and the heading. And GPS is not 100% accurate, so it will tell you a position which is, and then there will be some uncertainty. So you can think of a circular area around that position that the GPS gives you. You could be anywhere in that circular area, so to say. And likewise, there is some uncertainty in the heading as well. Talking about the other sensor, you have data from IMU, which tells you acceleration, but there's always some noise and some error because of the integration that I mentioned earlier. The third input is the time difference. So you need this particularly for the IMU. So when you have to integrate, you need the time difference since the last update. And of course, you need the map data because you have to localize with respect to a map. So you need map data, but not just any map. You need a map which has landmarks on it. So it has important information about buildings and other large stationary objects that can be treated as landmarks, and we'll see why. You also need LiDAR data for localization, and we'll see why. The algorithm we are going to talk about it something called particle filtering. It's nothing new. It has been used in robotics for a long, long time, and it's a very simple algorithm. The output that you require from localization is again position and heading, but much more accurate than the plain raw output that you would get from just a GPS. Right. So in this case, this localization is sort of solved in the sense that you can get very precise localization with the just just these sensors and simple algorithms. So how does particle filtering algorithm work? Like I said, you have a GPS, and the GPS has some uncertainty. So if I go back to the last slide, you see this circle around the car. So you don't exactly know where inside the circle the car is. That is, there is some uncertainty, but the GPS is also slow. So whatever reading you have, that is from the past, and it could be as far in the past as 100 milliseconds. So we are looking at stale data, so to say. So that this uncertainty and the data is stale. The first thing we do is we use the IMU readings to estimate how far the car would have moved. So if you see that the car is here and this GPS spot is here, this is the snapshot from 100 milliseconds back in time. Then you extrapolate this information using IMU readings. So you now have a different mean position, um, and which the IMU simply uh, does by integrating the accelerations twice. So you have a new mean position, but now you have all the more uncertainty because you had some initial uncertainty, but now because you did this calculation with the IMU, you have more uncertainty, right? So the first step, the second step in the algorithm is then to divide the GPS stop. So imagine that a GPS spot has been divided into smaller, finer grids, finer grid. So, for example, a typical GPS spot could have a radius of a few meters. So imagine that will be a few square, like if it's 5 meters, then it's like an area of 25 square meters, right? And now if you divide that into, let's say, a 2 by 2 grid, so there will be 12 cells or so. So 6 cells or so. So you divide the GPS spot into a smaller area cells. This is just done in the algorithm, so it's imaginary. And so each cell, and you want to see how likely each cell is to be the correct position, the true position of the car, right? And how do you do that? How do you find out which cell is the most likely position? So that happens in step 3. So you take every cell position, and then we also saw that we have a map where we have the exact, very accurate position of all the nearby landmarks, right? And we also have LiDAR data. So we imagine that if we were in this cell and we had this, if we were to measure our distance to this landmark, this would be so and so. And we also have the actual LiDAR data, which tells us how far away we are from from a particular landmark, right? So by doing this, by tallying your assumption about being in that cell and how distant you would be from a landmark against the actual lidar data, you can evaluate the likelihood of every cell. And this is all the algorithm is about. So once you do this tallying, you know which cells are more likely and which cells are almost unlikely. You can remove the unlikely cells, and then you have reduced that larger area to a smaller, more likely area. Right? This is what we wanted. So we have more precise information about where we are. Now this is just one iteration of the algorithm. You can iterate it again and again. And what happens is sort of what you see here on the right, this animation. So you see the cloud disappearing. So the initial red dots, the cloud is all the probable locations. So we can as human beings see that the green dot, which is the car or a robot. So we know where exactly it is, but the robot itself doesn't know, right? And so what the robot is does what does know is how far away it is from different landmarks or different obstacles, and using that information and then do that information and then iterating for a few steps, it's very quickly able to ascertain where it is exactly on the map, right? So initially you have this all the plausible cells or all the plausible positions which are all over the map, all over the white space, which is any feasible position, it's all over there. But just with a few cycles it's able to quickly convert that map close to the true position. This is very effective. This has been used in robotics applications for a long time, and this sort of solves the problem for the problem of having high precision localization. So this is basically how it happens. And in terms of what challenges are there for the algorithm, so the first one is, of course, we are talking about landmarks. So you know where the landmarks are on the map, but where finding the same landmarks around you, that requires identifying objects with the help of lidar and camera and radar data. So that is difficult because again it's object identification and it's an open problem. Then you also have to match objects. So if you have two landmarks on the map and you have two landmarks identified in the surrounding, then which one maps to which? The mapping between the map and the surroundings, that is also a problem which needs to be solved. And the third one is just the sparsity of the landmarks sometimes. So if you're driving on highways, for example, there aren't a lot of buildings or towers or bridges, then it's difficult to get those landmarks in the first place. And then there have been some efforts to use things like ground penetrating radars to look under the road. And if you look under the road, there might be some features of the some the geometry and the buildup of the soil beneath the road, and that can sort of give you a signature of where you are, you know, on a map. So there have been stuff like that, and so this is also still not 100% solved, but localization can is still way ahead of other components. Coming to route planning, like this is we have seen almost what the problem is about. So you have the current position from the last stage, you have the map data, and now you want to figure out which route to take. This is largely solved by third parties, for example Google, because when you want to do route planning, you not only want to find out a feasible route, you want something which is efficient as well. And that means taking care of things like traffic information, which won't be available to directly to us. So you need someone like a Google to figure out that information and give you the best route. So you need someone who can give you detailed HD maps, perhaps more semantically relevant maps, and you also need someone who can give you the traffic information. In terms of algorithm, this is often very simple. It's as simple as using an A star or dynamic programming just to find the shortest path, between 2 points. And there could be different definitions of what shortest means, time or fuel efficiency or something else. But route planning is relatively easy. So moving on, yeah, this is so. If I go back to the last slide, the output is of course sort of waypoints, which is like a sequence of coordinates that you have to follow, and this is sort of what route planning, sort of looks like. So the green track you say is the C is the route that the vehicle should take. uh, it has to be, in the case of self-driving car, it has to be a very well-defined region, not just a sequence of roads that you have to take, but you have to specify which lanes you have to take and stuff like that. But this is what the output will look like. Okay. So now coming to perception. Perception, if you talk about inputs, it's camera. Camera could be normal cameras. It could be stereo vision cameras, which let you perceive depth to some extent. It could be LiDAR or radar. In terms of output, what we want to find out is the different object types, uh, and their distances, their bounding boxes, free space. We mentioned all of this earlier. And this is sort of the stumbling block for computer vision, because you can do a lot of things with a lot of these things, object detection and bounding boxes with computer vision, but it's not as accurate as you would like it to be for a self-driving car. And deep learning has certainly pushed the boundaries a lot you know ahead in object detection and bounding boxes, and we'll see a few examples. But this is the part that is still open. You also need to do this at scale and very high speed, right? So there could be like 1,000 objects in a scene that are relevant to the driver to drive safely. And so you need to identify all of them, and you need to do that quickly. And a lot of computer vision algorithms will use some sort of a scanning method, some sort of a window that they will scan all over the image and identify objects, and that can be relatively slow. So this is where we are sort of benefiting big time from deep learning. So first of all, it's a difficult problem to formulate mathematically, and that is why it has been solved for such a long time. Like, how do you describe an object mathematically? So that has proven impossible, and that is why we have these data-driven algorithms that can just learn the features of what a car looks like, what a human looks like, what a cyclist looks like. So that is the first issue. But there are issues about illumination, contrast, shadows, even reflections, and of course, occlusion, like things behind, being hidden behind other things. And if you think about all those situations, it becomes evident that computer vision, it's very difficult for old computer vision or classical computer vision to deal with all those variations and still perform satisfactorily. So uh, you know for example, a simple thing like lane detection on the road, lane markings, that could be pretty difficult for computer vision, because of all the variations in lighting and shadows and geometry and stuff. And even they could have gotten faint over time, so that is an additional issue. And when we talk about perception for just the object detection part of perceptions, there are hundreds or thousands of things that we want to just identify, like vehicles, pedestrians, and lane lines and road markings and all of that, right? So computer vision algorithms are pretty advanced. Like the output you see here is just from a normal computer vision algorithm. It is using some sort of an edge scanner or edge detector to find all the edges in an image. But the task is not done. So we as human beings are able to piece together the edges and see, okay, those edges make up, and say that those edges make up the car, and there are some edges that make up the arrows on the road. But these semantics are difficult for any algorithm. So the next step would be to somehow group these edges into meaningful objects, and that is difficult for traditional computer vision. It has been done. There are algorithms, some very advanced ones as well, but they are still fragile, right? And that is what causes the stack to fail in certain situations. So what's up here is a demo of computer vision algorithm. You can see that it is performing okay, right? It's not bad. This is a simple computer vision algorithm, and it's just able to get detect where the lane markings are, and then it's able to interpolate them and sort of create a region where uh, the car can drive safely. So this is just an example of, you can use computer vision, but if you run the whole video, you'll see situations where it fails, and you don't want that to happen. Yeah, so some of the challenges, you see three different images on the left. There's a screen grab where there are some trees casting shadows on the road. and then you have the edge detection part, where the shadows are showing up as bright edges, of course. So you have to get rid of them before you can start detecting edges with computer vision alone. So if you see on the image on the right hand side, that has gotten rid of most of the noise. It has lane lines, and, which look quite thick, but there still needs to be a lot of processing before you could actually narrow down to edges or lines that make up lane markings only. So this is difficult, and this is fragile with computer vision. And this is what happens when you use a computer vision approach. There's very little context, and things are written in a way which makes it easier for them to break if if something falls outside of the range which you estimate it to be. So for example, in this case you see a twisted region, which is because the algorithm has messed up somewhere. It's not able to detect the lanes correctly. And there are ways around it. You can use some smoothing across frames. Uh, you can filter out candidates. If there are candidates, you can filter some of them out based on laws of physics. For example, you won't have a car hanging in the sky, so, or you won't have a lane that is above a certain horizon, stuff like that. You can also fuse lidar sensor data, which helps a lot because you know which planes are vertical, which are horizontal, and stuff like that. um, but the issue remains, and this is how a computer vision pipeline for object detection will look like. So in this case, we are looking for cars. So in most computer vision algorithms will depend on edge detection. So you have an image here, and then you apply some sort of an edge detector, which tells you how the edges are oriented, and then you feed it to some sort of a classifier, which tells you whether the edges are likely to have come from a car or something else. uh, but then if you want to do this object detection at different scales, so you need to scan the image, the window based scanning approach I talked about earlier. So you have to do that. So this is how it has been traditionally done. Of course, this is this can fail in multiple ways. uh, what you see here is an output of such an algorithm. uh, there are different improvements here. There has been, there's some sort of temporal smoothing. What you see here in blue is some sort of a heat map. So you are using information across different frames uh, to, a- find areas where, the probability is really high of finding, detecting a car. So that is helping, but as you see on the next slide, there are instances like this one where there are two overlapping cars, and then the expectation is that you should have two different bounding boxes, but this algorithm is not able to do that, right? The alternative is to use a deep learning approach, which can be very precise. For example, even with the small objects like road signs and speed signs, uh, it can get them right. And with enough training and all sort of variations in your data, you can build something which can perform very well. So at least you don't have to iterate on the algorithm so much. You can iterate on the data, but you don't have to come up with new features, new algorithm every time you want to have an additional object or an additional scenario that you need to identify. This is where sort of the deep learning part of AI is helping improve things. When it comes to object detection, deep learning is like breaking all records. There are different variations like YOLO and SST, but in this simple picture, you can see that there are at least a dozen objects which are clearly identified, and then you also have their bounding boxes identified, right? And deep learning is just very good at this. Of course, you someone has to like painstakingly build that system and train that system. But then if you have enough data, you can build a system, you can build a deep learning system which can anytime beat a computer vision system at stuff like this. And bounding boxes are super important for driving, so this is where deep learning is a clear winner. And then there's stuff like this which is almost impossible with old computer vision, just purely because of the speed, concerns, the speed at which they can run, and also the sort of quality the output they give. uh, but with deep learning, what you see here is a scene which is almost perfectly segmented. This is just the data from the camera. If you fuse the camera from lidar and other sensors, you can get a far better picture. But with just one single camera looking at the scene, we are able to very clearly identify the outlines, and this is what semantic segmentation is about. uh, this is pretty doable on normal laptop, or on a simple computer. So this is where deep learning is again pushing the boundaries, right? So if you have the data, and of course that data has to be like, with a lot of effort, it has to be labeled and the outlines drawn in that data. But then you can build something which can perform stuff like this, right? Not only in 2D object detection and 2D perception, but in 3D perception too, where the traditional approach has been using classical algorithms to identify objects in lidar cloud. So the traditional approach has been to use you know so what we want to identify is the bounding boxes for these objects, 3D bounding boxes. And the how the algorithm works is sort of in four phases. So you take the raw sensor data, then you try to remove the ground, like the road and anything which is a horizontal ground. So you try to remove the ground plane. So any point that is part of the ground plane, that has to be removed. Then you have to cluster those points. Now you need an algorithm that can cluster points belonging to one object together. So you need to do some sort of clustering, and then you have to do some sort of classification to identify what those objects are. So there are different objects, but what exactly those objects are. So you need classification, and then of course you need tracking. And this is like, in a conventional approach, this will be different algorithms sequentially doing this thing. But there are deep learning alternatives as well, which seem to be performing as well as the conventional approach, and sometimes actually beating them. So this one, the animation you see here, is actually from a 3D neural network that just works end to end. So there are no stages in the neural network. You feed in the lidar data, and it gives you sort of the 3D bounding boxes of where objects are in the lidar data. And this is very cool because, again, like, even 2D perception is difficult, and 3D perception is even more difficult. So building something which is accurate is very difficult, but certainly possible has been possible in the last few years because of deep learning. This one here is again a demo from NVIDIA, and right, right. So I'll provide the link for the full video, but the idea is that they are using a deep learning approach in a neural net that can identify the 3D bounding boxes, and it seems to be working pretty well. So perception, still remains open, but there are advances. Every year you have some new state of the art results. So the hope is that gradually we'll reach a point where we can perform satisfactorily. We can identify most of the objects and their outlines in real time, um, and then we can sort of start thinking about cars which are much safer and ready to drive in any sort of environment. Prediction, again, prediction is relatively simple given that you have all the sensor data from the previous stages, so you know what objects are out there, and you are also sort of able to track those objects. So prediction can be relatively simple. uh, you know so you have the bounding boxes and objects, and you just want to find out where those bounding boxes or objects will be in the next few seconds. You can use the laws of the physics or just the historical data to predict which direction they'll be moving in, and whether or not they'll be turning or not. But again, there is two alternative competing approaches. One is the classical approach, a model based prediction approach that you see on the left, and on the right you see a data driven prediction. So in the model based approach, for example, in this scenario, the blue vehicle is the ego vehicle or the self driving car, and the green one would be any other vehicle. And what we want to predict is whether the green car will go straight or whether it will take a right turn. And that is how we'll we will plan our own trajectory. So in the model-based approach, you have a model for every behavior. So in this case, there'll be two models. One model will be for cars going straight. The other model will be for cars that take a right turn. And of course, from the perception stage, we are getting data about how this car is moving, and we'll match that data with both models. So the model that says the car keeps going straight will say that the velocity will be in just one direction and stuff like that. The other model will predict that the velocity will have two components, and one of the components, the right component, will keep increasing. So you can start with these two models, and then you can weigh them equally. You can assign them equal probability, and then across a few time steps, you can keep track of the actual data, and then you can reweigh the models. And after some time, one of the models will have a very high probability, which will probably be the model for turning right. And so at that time, you just discard the other model. This just require an explicit model of every behavior. So it's a four-way intersection. Then you require other types of model, and you have to you have to factor in all sorts of feared failure behaviors and everything. So this is a classical approach. The other approach would be to just keep collecting a lot of trajectories. So because self-driving car is collecting data all the time, so you do have data on how trajectories look like, how other vehicles behave in time. And if you have all of that data, you can build a neural network of some type. And then when you see this green vehicle, you can just input this vehicle's current state, which is whatever data you're getting from the previous stage, which the perception stage. So its velocity, acceleration, direction, everything, you can feed that to the neural network, and the neural network will then help you, predict what the velocity and acceleration and everything is going to look like in the next few seconds. So basically, it tells you what the trajectory will look like in the next few time steps, given the current state of the car and given a lot of historical data. And this is exactly what's people at Waymo have done. So they built a recurrent neural network, and they fed it a lot of trajectories, and then they start querying the neural network for new trajectories given some new data, and this seemed to perform pretty well. So this is also an option if you want to do prediction this way. This is also an option. And why would we at all want this sort of data driven approach? Because the model based approach is it needs you to handcraft every single scenario, which again at sometimes becomes bottleneck. Right. So apart from predicting the behavior of cars and trajectories, you also want to predict stuff like how humans will behave, and we touched upon this earlier in the talk. But simple cues like what is the pose in which a person is standing, that will tell you about something about what actions they're likely to take. So stuff like that can also be predicted with there are networks out there that can be trained, and that can predict pose, and then from the pose you can guess what the human is likely to do or not do. uh, you can also build networks that can, instead of just predicting trajectories, they can tell you in which direction the motion is happening. Right. So just by looking at camera data and without radar or anything, you can build optical flow models that tell you how vehicles or pedestrians are moving. And this is also something that can replace some of the conventional approaches. Yeah, when it comes to planning, like I said, it happens in space and time, so there's not a lot to offer in terms of plain deep learning for planning alone. So I'll just skip over this slide because this is all the stuff that we discussed earlier. uh, Output of the planning is of course going to be a sequence of waypoints. uh, Control, we talked about earlier. There are two algorithms, two alternatives. One is called PID and one is called MPC. PID is just looking at the current trajectory and the desired trajectory, and takes the difference and it tries to make the difference small. MPC projects your current trajectory in the future, and then look at the difference not only at the present time step, but also what it would look like in the future. And from it optimize finds the most optimal controls, the combination of brake and acceleration and everything, to so that your desired trajectory gets followed. right? So very quickly, that's control for you. Uh, this is sort of how controls looks like. So you plan a trajectory. So there's the yellow trajectory, which is the desired trajectory, and there's the green trajectory, which is your actual trajectory. And at every time step, you sort of plan your green trajectory a few time steps ahead. Then you follow it for just a fraction of those time steps. Then you discard it. Then you plan again, because the yellow trajectory also keeps changing from time step to time step. But yeah, this is how control looks like. uh, Now, what has changed is that some people are experimenting with solving the prediction and planning and control problem together, which is like having an end-to-end system. And there, so this is not quite deployment ready, but there have been like simulation scenarios that people are trying to solve with using, for example, reinforcement learning, right? So there's a short demo here where there are two cars, and they are turning to basically first of all steer correctly. And right, so essentially what's going on is that there are two cars in a simulator, and then they're learning to sort of wait for the other cars to pass and then safely take a turn. And they're also learning, so the first part is planning, but they're also learning to have the right controls, so that initially the cars are going zigzag, but over time they learn to follow a smooth trajectory, and they also learn how to avoid other cars. Sort of planning and control in one go using reinforcement learning. This is more experimental stuff, but it certainly like seems promising. All right. So if I have to put all of this together and show you a glimpse of how what it looks like, especially using a deep learning approach. So here's a demo from NVIDIA. Yep. So again, the link, I'll share the link in the slides, and you can watch the full video. But that looks super cool, and this is awesome because when you look at the details, so they are using deep learning, like predominantly deep learning based approach. So you saw the vehicle changing lanes, and there's a lot of stuff happening behind the scenes, like lane identification and free space estimation, and like a lot of complex driving scenarios, urban driving. So their approach, NVIDIA, like I said, has been predominantly deep learning driven. So you can look at the video, but that's certainly seems cool. And all of this is currently possible. Maybe this is a cherry picked example, but if we keep pushing the state of the art in perception and computer vision, then you will have many more examples, like even in denser environments. And there are a few videos later on in the presentation that do that, like driving like this, but in more dense urban areas. But this is what is currently possible. Right. So because we are actually slightly over time, so I'm going to like speed up a little bit. So this part is about experimenting and getting your own sort of lab setup if you want to experiment and understand the field a little bit. So first of all, there are a few talks and courses if you're not familiar with. So it's a mix of things, like this control, there is the computer vision, there's deep learning, uh, and there could be a few other technologies mixed in there. So if you want to get a hang of any of these things, then I'll suggest starting somewhere here at the bottom. So you have these courses at the bottom. The first course is just an introduction from Udacity and Baidu. So what different components are, just very close to what we just saw in slides. The second one is more like a toy environment where you can get you know somewhat hands-on, but it's not very realistic. But yeah, it gives you an idea of the sort of problems you solve. The third one is actually a very hands-on course where you're actually not working with a real car, but as real as it gets. So you're working with a simulator, and then you are controlling the simulator using ROS, which is robot operating system, and AutoWare, which is the piece of software. So you're essentially communicating between the simulator and these two pieces of software, and this is behind the scene ROS is running the different components of your algorithm. The nice thing is that you can actually build different components that we talked about, so localization or perception, whatever you want to build, but you can also use existing components that AutoWare offers. So if you want to just experiment and you don't want to build all that stuff, then get started here. The fourth course is from Udacity. It's a narrow degree, it's like a 6 months course, which again covers everything in terms of computer vision, deep learning, and control, and sensor fusion, a little bit of sensor fusion um, that you need for self-driving cars. At the top, you have some very interesting talks, which just give you a high-level idea of what is currently going on in the field. So it's not exactly what you find in news articles, slightly in depth, but uh, yeah, I mean, yes, these are some amazing talks. So I would highly recommend the first talk from Andre Karpati, who's with Tesla right now. Uh, there are more details. I'm going to actually not go into the details of the talks, but they are there on the slides. So, for example, Andre talks about stuff like dealing with these variations in during object detection. How do you deal with every slight variation? And because Tesla is also not using lidar, so he also goes into details of if they're not using lidars, then how do they how are they performing and what is sort of their plan, and he'll show you some examples along the way of how their computer vision system is on par with lidar systems. So all of that in a short power pack talk. It's a short one, very interesting. And then there are a few other talks. I'm going to skip over them, but many of these are actually sort of demos where they're showing you a car driving around, say, an urban area, and then there's some commentary at the back, so you understand what sort of common challenges they're dealing with and how they are solving them. Some of the solutions are scalable, some aren't, some are just hacks, but yeah, you get to you get a sneak peek of things. Right, and then there's another one from the CEO of Voyage. This is interesting in its own way because it talks about some of the opportunities as well, not just the challenges. Like some companies that are building services on top of self-driving cars. So, what are those services? Where are those opportunities and stuff like that? That is there. And then there are a couple of other talks. This last one, which is not actually a talk, but a series of short videos, one of which I played earlier, is from NVIDIA. This is highly recommended because they show you how they're using deep learning to solve every small part of the larger stack. Like, so something as small as just identifying when someone is driving, with a high beam. So it's nighttime and there's a driver coming from the other side and they're causing glare. How do you identify that it's glare, and then how do you mitigate that? So it's very important, a small problem, but important to solve. So how are they doing it? And then they have this huge system with a lot of neural networks, each solving one small problem. So one neural network could just be identifying lanes and then crossings and stuff like that. Sorry. And the bird could be doing other types of object detection. A third one could be doing this clear detection. So why is it necessary to have so many different neural networks? And this is something that Andre Karpati also touches upon on his talk, in his talk. But yeah, it's important to know. And then there's an interview from Commodity AI. They are also different in a way because they, they have very slightly different approach because they want to sort of retrofit existing cars with systems that can drive them, and they also have a purely deep learning and computer and a deep learning based approach, and they don't use lidars. So it's interesting in its own way. In terms of what you can do after looking at the talks and the courses, you can try to build something, like something in a simulator perhaps. So you can use AutoWare and ROS, like I mentioned. There are a bunch of simulators I'm going to show you in a minute. You can set up one of the simulators. Uh, so I'm going to skip over the courses. These are the details of the courses, but you will definitely find them interesting. Uh, right, so this is the ROS course, and the simulator have also gotten pretty good. So it's a lot of detailed simulations, everything from physics to the graphics is pretty detailed. Right. So I'll just skip over to what else can you do. So you can use simulators, you can do stuff that I'll show you, shortly. But if you want to collect data, so of course, building a full self-driving car is not something an individual can do, but you can have a mix of real-world data and simulated data. So there are, sensors which you can use and collect a lot of uh, data cheaply, and that also gives you some validation. So if you're building an algorithm which works in the simulator, will the same algorithm, maybe with a few slight changes, also work for real data? So if you want to test that, what you see on the left is a stereo camera. This one is from Z, but there are many other alternatives. So just grab a stereo camera and mount it on any car, and you can collect a lot of 3D data. You can also have a small device. It's called a Panda from Comma.ai. It lets you capture a lot of messages. So we talked about how the typical car will have a lot of different control units, ECUs controlling different parts of the car and how they communicate over a network. So if you want to tap into that network and read those messages, this is the device you need. It's very cheap, and you can just connect it to your mobile phone, and you can get a data. Of course, the actual data that you get, that will depend on the make of the car, the model, and how old it is, and just basically how much data they are exposing over the network, and how much. Panda also has firmware, so which firmware supports decoding what type of data, but you get the idea. In terms of if just working with the simulators, which I find is like a pretty good way of doing research and exploring things. So there are a bunch of options, especially two stand out. One is this one, a deep drive from Voyage. I personally have used Carla for a long time, and Carla has been evolving at a rapid pace. So every few months, there's a like big milestone and big release, a lot of features. It's pretty detailed. It has like very easy to set up and be very easy to control programmatically. So even before you build anything, you can just set up the simulator. You can fire up your Python interpreter, and you can write a small script, and you can start controlling things, which is cool in itself. Now, when you're building things in simulator, you're building algorithms. Of course, at some point you would like to debug them, and debugging isn't easy when you have this huge amount of data flowing in. So there's a tool from Uber called Uber AVS that you see here. So you can install Uber AVS, and that lets you replay. So when you're simulating things and your algorithms, maybe your algorithm is not correctly working 100% of the time, what you can do is keep dumping the data. So dump the input, dump the output, and by input, I don't mean probably the raw input, which is the camera footage, but the process input, like what is the output of your perception module, perhaps, right? So there are other objects, how fast is your car going, how fast are other objects going, stuff like that. So you can dump that. You can also dump a lot of other data, and then you can view and replay all of that data in Uber AVS. And this is perhaps the best way to debug deep bugs because you can't do that in real time, right? And then there's another alternative, called Apollo from Baidu. So it has some of the features of Carla and you can say Uber AVS combined. It's actually a full-fledged driving system. So this is designed in a way that you can install it on a real car with some hardware and make it self-driving. But what is more interesting is that they have a standalone simulator where you can, you know, you can simulate things, and you can also hook it up to different other pieces of software like AutoWare and ROS and stuff. So this is also I haven't personally worked with Baidu's Apollo simulator a lot, but just going by the feature list on their site, it seems something worth trying out. Right. Finally, when you are doing something like this, very often you want to build an algorithm, and especially if it happens to be a deep learning algorithm, you don't always want to collect the data, because collecting data is not so straightforward, even if you're doing in a simulation, right? So simple things like you have to skip frames, then that becomes difficult. So here's a list of data sets that have been curated from by others. So you have traffic science, you have even this semantic segmentation data set and stuff like that. So there's a long list, and in fact, if you open the last link, so it's a very comprehensive, curated list of almost every data set that is relevant to self-driving cars, and that has been released by companies like Waymo or Ford or Baidu. So anything out there that has been curated by scale.com. So that list is there. So if you want to train your algorithm, maybe download the data from here, train the algorithm, and then test it in your simulator or test it with a little bit of real data. Yeah, so I think that's it. I'm going to stop now because we are actually 15 minutes over time. I'll very quickly, if there are any questions, we can take the questions now, right? So I'll stop right here. So, any questions, most welcome. I'll happy to answer. I'm happy to answer. You can either type your questions in the chat, or you can unmute yourself and speak in the microphone.
Hi, Farhan. Thanks for your great talk. Yeah.
Thank you for having me.
Okay. So, for the first question is related to the sensor, because
Right.
from your chart, there is no sensor um that can have all the functionalities. Particularly, I mean for the waiter, right? For the waiter,
Right.
I know like the radar can be is good for all conditions of a waiter, but there is low spatial resolution, and it's not so
Right.
robust to the noise. Yeah.
Right.
So if it's in the bad waiter condition,
Right.
right?
So bad weather, like with humans, I think that is still unsolved, and that is not so high on the priority list, because even in good weather conditions, we find it challenging to solve. But with bad weather, one of the sort of so you're totally blind, right? If the weather is bad, you cannot depend on the lidar, you cannot depend on the camera, you can use the radar. The only other thing that comes to rescue is another type of radar that I talked about, which is like some sort of ground penetrating radar, and that gives you some sense of where you are on the road. So
Hmm.
it's an open problem, and yeah, a difficult one to solve.
Okay. And
I mean, you can, people have tried, I think, with magnetic sensors and stuff, but that is not really scalable. And then you're not truly like building a self-driving car. You can have sensors embedded in the road, but that only goes so far.
okay, thanks. And about the planning or about the prediction,
Right,
particularly, I mean, in some countries they even don't have traffic light, and
right,
I mean, the drivers they even don't follow any rules.
right,
So for that case, how do you have a proper model to predict behaviors of the
right,
drivers?
right. So again, I
Yeah.
think it's an open problem. Um you know, I mean, so that definitely happens here in India a lot of times. So the traffic light is not working, or people are jumping the traffic light. Uh, so if you want to test your vehicle in such a place, then obviously at the very least you need to have a system. First of all, you need to keep your speed in check, and then obviously when you're building, if you're using explicit models, then you have to take into consideration stuff like that uh,
Mm-hmm.
for safety sake. And if you're using a data driven approach, then obviously it's a common issue, right? So it's not something which is if you're collecting data, then you won't have a lot of those trajectories where someone skipped a light. But because you are aware of such a situation, then you have to perhaps use additional synthetic data, or you have to artificially create copies of those instances where someone broke the traffic rule and skipped a light, so that you have enough representation in your data set.
Mm-hmm. Okay. And the last question is about the control. For example,
Right.
if there's any like some malfunction of your car,
Right.
and somehow you just cannot control it as you expected. Yeah. So
Yeah.
have
So
this
if
also been considered? Yeah.
yeah, so there's a whole there's a whole issue of ethics and safety. And if you take one of these courses from Udacity, so there's this entire module on how to design the safety aspect of the car. So obviously if one of the things which, for example, aircrafts do is have some sort of redundancy in the system. So if one control is not working, you can rely, or one sensor is not working, you can rely on another one. There has to be a supervisory system that just keeps checking the health of everything else. uh,
Mm-hmm.
Assuming that you have that redundancy in place, you can build a system that can take over. So for example, if you detect that one of the sensors is malfunctioning, then the very least you can do is that have another system that can take over and safely bring the car to a halt, perhaps on the side of the road. So that has to be there, and that is I think any real self-driving car which has to go on the roads and have to get permission from the regulators, it has to have that safety system built into it, the redundancy built into it. And it has to, so there are already existing safety standards for general uh, automobile manufacturers, right? So it has to
Uh-huh.
follow all of them, and there are additional standards that are coming out. I forgot the name, but I think it was Voyage probably that came out with sort of manual and guidelines on what those additional safety requirements should be for a
Mm-hmm.
self-driving car.
Okay. Okay. Sense.
Sure. Yep. Are there more questions? Okay. So if you don't have a question right now, but if you come up with something, so my email is there in the invite that you would have gotten, so you can email me. I'll try to answer the questions. Cool. Thank you all so much. Really, I appreciate you taking time out and attending the session. Have a nice day. Bye.
Thank you. Bye bye.
Thanks. Bye.